Well, hello. Good morning still. Thank you for coming right before lunch to our talk. My name is Manohar, and so I was a PhD student at Martin Odersky's lab, working on programming languages. And then after I finished my PhD, I meandered around a bit, did some research with Microsoft India. But then, I decided academia was enough, so I would switch. I would switch to the industry. And the main reason to switch for the industry for me was, well, it's basic common sense. You earn a lot more money, right? So I really wanted to find out the true academic that I was. I wanted to compare. Do I really earn more money, and how does it stand, and how does it stack up with respect to, I guess, the rest of the people. So I went and asked my colleague Jakob, hey, Jakob, how much do you earn?
Yes, so I'd already been in the industry for a while, and I was a bit surprised when Manohar asked me because we don't really talk about this in the industry. So what we did is, wrong order of slides. We went to talk to our CTO, Dimitar, and asked him what we should do, and he suggested, well, you know what, instead of revealing everyone's salary, why don't we just try to get an average? So we came up with this basic protocol calculating an average. The problem here is it doesn't really solve the problem that we would like to hide our individual salaries. Either we need to all reveal it, or we need to trust a third party to have access to all of our salaries. So instead, we can understand why he did not want to reveal his salary as well. Instead, he suggested we could come up with a different kind of protocol, a protocol that is privacy preserving. So with some clever mathematics, we can calculate the average without revealing our individual salaries. So here's how this protocol goes. Every one of us, we have a secret number we would like to keep secret, which are the numbers in red you see here. We each also generate 3 random numbers. All numbers must be random, but the total sum must be 0. We'll get to that in a minute. How would we model this in Scala? Well, the first thing we should introduce is 2 types. One, the secret value we would like to represent. In this case, it's just an integer in this example. And then the concept of a shared number. So the shared number is the list of secret numbers. It corresponds to what you've seen on the left here, this sequence of numbers. And the key part here is, in this model in Scala, is every element of the list is only accessible by the corresponding person. Then, we have a function that generates these random numbers, and we generate 3. One for Dimitar, one for myself, and one for Manohar. In a table view, how would this look like? A bit like this. We have, again, the parties involved in the computation. On every row, you have the shared zeros, so D, J, and M are actually all sum up to 0, and our secret data. Then the protocol goes as follows. We each sum up our shares of zeros, so our own share and what we have received from other players. This gives us a shared sum. This value here is published to every other player. And the final sum of all values will equal the sum of all our private data. Here is we can see in callout, as I just mentioned. As a numeric example, it might be more illustrative to see how it works. We'll get into the security in a second. We see here every row indeed sums up to 0. All numbers here have been randomly generated. And if we sum up all the shared sums, we arrive at the same sum as if we had summed up all our data. Now, why does this work? The key thing again here is that all the shared zeros, all the shared the triplets we generated, they all sum up to 0. So that means the total sum gets cancelled out. And why is it secure? Well, it's because no player has full information. If we look at the point of view of Dimitar, Dimitar knows what's in this row because these are the numbers that he generated. And he knows what's in the column because these are the numbers that he has received. For myself, I have a different view of the world, and Manohar again. So unless someone is able to intercept all communication, there's no way to find the original secret data. How will we model this exchange in Scala? Well, we need to introduce what it means to add numbers first. So there's one concept which is adding shares, so adding parts, adding essentially two numbers, D and J. What that means, it's just an element-wise addition of the individual secret numbers. And then we also need to introduce the concept of what it means to reveal a value. And that, again, is just summing up all parts of the all individual secret shares. Then on the right of the table, you'll see a one-to-one mapping of the sections of what I just described and how we can model that in Scala. So again, the green part, we generate the 0 shares. The red part, we model the secret data we have, which we would not like to reveal. And then finally, in the shared sum, we use the additions we just defined to compute the final sum and reveal it to the world. This, for the sake of the demonstration here, we have addition and secret addition defined on element-wise. Of course, with some neater Scala tricks, we can make this look much nicer. But for the demo, we did not do this.
So happy as I was to now know the average of the salaries, I also learned something new. So what you have just seen is an example of what is known as secure multi-party computation. So this is actually a subfield of cryptography where the goal is to create protocols or algorithms for different parties to compute a joint function such that without revealing their private data. So to illustrate this again, what it means is you have secret shared data that is sort of hidden. Only I know my share. But when we join it together, we get something. We get a result. So we can, of course, go back and forth, right? The idea is to compute a joint function which gives you something that you are looking for all together. So, well, how does MPC work? So what we have seen is an example of addition. So as we said, an average is you reveal a sum, and you get the and then you compute the average by dividing by the number of people. Well, addition is great, but it's not enough, really, is it? We may need a bit more. So what about multiplication of secret values? So multiplication is a nonlinear function. How would we do that? Well, I won't go too much into the exact details about it, but the general idea is that we can also do multiplication, and please come talk to us to find out more. But the main idea is that we can do multiplication, but to make it a bit more efficient in terms of performance, we introduce the concept of a trusted dealer here. So remember in the earlier example, so Jakob, Dimitar, and myself, we created our own shares of 0, and then we exchanged it amongst each other. In this case, we rely on Mr. Question Mark here to do that work for us. So Mr. Question Mark is only involved in giving the shares to us, but when we actually do the computation, he's out of the picture. So this is what we mean by trusted dealer. And what do these shares allow us to do? Well, basically, for multiplication, this Mr. Question Mark needs to give us some pre-computed values, which we use for doing something which is called mask and reveal. And in the case of multiplication, this is known as beaver triplets. These are a lot of new words. Don't worry about it. You don't need to know much about the words. Just, as I said, come talk to us to know more. I just put these here because when you see the videos, it's nice for you to go and Wikipedia them. Great. So we have addition of secret values. We have multiplication of secret values, which means we can actually do quite a lot of things, because with addition and multiplication, we can express any polynomial. So which means we can do actual, serious, interesting stuff. In particular, we can do things like linear regression and logistic regression, because they can be expressed as polynomials. Wait, how is exponential a polynomial, right? Well, I don't know if you remember your calculus classes. For me also, it was a while back. Thankfully, I also learned that in addition to my average. Exponential, you can approximate an exponential function using something like a Taylor polynomial. So again, back to polynomials. So it all kind of works out quite neatly. And so these are just mathematical formulas, but what you really can do once you have such functions is classification, right? So, I mean, I wouldn't want to be one of those chihuahuas there in public, right? It would be quite unfortunate.
You get confused with a muffin.
Yeah, I don't like to be confused with a muffin. Yeah, so when we get the polynomials, then we can actually go to the real world, and MPC is actually valid and has valuable use cases in the real world. Let's look at a sort of a general picture of the different kinds of use cases that we may have here. We have different sectors: financial services, healthcare and genomics, digital advertising, defense and manufacturing. So basically, anytime you want to compute something, but you're not allowed to share data for various reasons, right? The data is sensitive. They can be legal, they can be just computational, they can be anything. You can use a technique like ours, like MPC, to do this. So let's go into one of the bank cases. So this is a case that we studied with ING. It's simple. ING is a bank. It has very rich customers in some of the richest countries in Europe. And what it wants to do is build some sort of credit scoring model on all its clients. But the problem is the user data can't cross a country because of various laws. In particular, I'm sure you've heard of GDPR, which was maybe one of the biggest things in the last 2 years in terms of privacy-related computations, legally speaking, of course. So if you have something like a multiparty computation engine, then you could still build your model without the data having to cross borders. Let's look at a slightly more fun example. Let's say you have the usual Russians and Americans, maybe Chinese now because that's what the world is like currently, who have satellites on Earth, and they don't want to reveal where the positions of the satellites are, yet they don't want to create destruction in the outer space. So you may want to secretly detect collisions. And this is not an imaginary example. We had such a thing happen in 2009. It's just nice to avoid such things because this actually then resulted in the International Space Station having to maneuver just to avoid the debris and stuff like that. So this is not a joke, really. It is serious stuff. And so, of course, we also we know that computationally we can preserve privacy, we can have the security, but it's also nice to know that we consulted lawyers, and Baker McKenzie are experts in this area, and they have concluded as well that we don't violate the GDPR. So that's also great news, legally speaking. If you're interested in solution, this is definitely one way to go. So we showed you a short example of an embedding in Scala. We have done a bit more work in our prototype here. We have multiplication involved, so even if you don't want to come to talk to us, you can definitely see the code and find out how it works. Great. Well, thank you very much. Is it enough, though? Is it enough to have a direct embedding? So what does a direct embedding give us? Once more, what have we done here? We've taken code. Now we can write code in a declarative or machine learning style. We can write machine learning algorithms as if they were written in Scala or Python or your favorite language. And due to the embedding, we were able to get the security multi-party computation protocols running. But actually, in reality, we need a bit more, right? Because in reality, the computations are distributed. They're not just an array. And so we must target a runtime which runs securely in each of the parties. So that's one reason why it's not enough just to have an embedding. The other reason, actually, more fundamentally, mathematically speaking, is we need to do some static analysis of our programs such that we can sort of optimize for memory and for communication purposes. And we also want to be able to compute some statistical distributions, which we will get into in a short while.
Yes, so rather than having only a library, we decided to write a compiler. The idea here is that we will take a high-level language, something a data scientist will be familiar with, something that looks maybe like Python, MATLAB, so linear algebra style, and this high-level language will abstract away completely of any kind of low-level MPC details. So anyone could use this language to write a program as they would usually do. The compiler will then generate, transform this program into low-level primitives that get distributed and actually run. So that touches the case for the real-life deployment. And then, of course, there's also a lot of static analysis that is done, kind of what Manohar just mentioned. I'll give you a quick overview of the system we have at Infer and how the compiler fits into this distributed reality. So there are a couple components involved to do real-life secret computation. We'll start going from the bottom, work our way to the top in terms of abstraction. So at the bottom we have players who, so players is the technical term for parties who have data. We have the players who have access to some data which they would not like to reveal. Each one of them will run a virtual machine on their system that has access to the data. This virtual machine can be verified that there is no data ever leaked out. Then these virtual machines will do the number crunching. These will actually run the secret compute algorithm. To receive the algorithm, this is where the compiler fits into the picture. We also have the trusted dealer, which is what Manohar mentioned earlier, to support some more advanced computations. And just to make it a little bit easier to use, there is also a nice front end. The compiler is hosted by Infer. The engines, the things running the programs are, of course, hosted by customers. So how would it look like if we want to run a computation? Well, an analyst through a front end would submit a computation to the compiler. The compiler compiles the program, distributes it amongst all players. Then the trusted dealer generates random numbers, sends them to the players. So the trusted dealer knows, of course, what random numbers to generate thanks to the compiler and a cooperation between the compiler and some engine components. And then there is the computation actually starts amongst the engines. There's a communication, exchange of data. And finally, the end result gets sent back to the one who submitted the operation. Now, this trusted dealer, I just want to take 2 minutes to dig into detail here while this is still secure, because you could think like, hey, we generate random numbers. Why should anyone trust us? We could spy on you right after that. And the key thing here is you'll notice that after the trusted dealer has sent out numbers, there is no more communication with the trusted dealer. So that means we do not have any knowledge of any data that leaves the data sources, so that even if we had a malicious intent and knew all the random numbers that we generated, we would not know any intermediate results, and there would be no way for us to reverse what comes out of it.
So that was the distributed part, the overview of the architecture. Now, well, why else do you need a compiler? So we're talking about the actual mathematical properties behind this. So this is going to be the most technical part of this talk, but I just want to give you an intuition about what it means to mask numbers. So what do we mean by masking numbers? Well, earlier in the example we had, we were masking our salary by generating these random numbers and adding them up, such that when I look at a number, I couldn't really make out what the initial or the original plain text value was. So, of course, we did with integers, right? So how do we mask integers? Well, it's a relatively easy thing to do. an integer, let's look at the 64-bit integer. So we have a fixed size, we have a fixed range, and which means that I can uniformly at random pick any integer and add it to my plaintext. And so how do I know that this is secure enough? Well, the security model is given to masked values. Can I differentiate them? Can I distinguish one from the other? And in this integer case, I can't, because everything is picked uniformly at random. So I'm none the wiser really with masked values. And this gives us a property which is very nice, which is called information theoretic security. So this is sort of the best of the best that I can do. Unfortunately, in real life, we have floating point numbers, and those are slightly harder to mask. So I'm going to try to give you a bit of intuition as to why that is. Well, in floating point numbers, the first thing is the fixed range is something that does not exist. We have basically, it's essentially real numbers. And so how do I mask real numbers? Well, the best I can really do is to take my plaintext and have a normal distribution around it, and then pick something in that. Now, if I pick a distribution that is too small, then I may be able to distinguish two values. And that's sort of on the left with the double camel hump here. So think of me picking two different values. I think here it's sort of 0 and 1. And I picked a small distribution, not a big variance. And so the only way these two values are distinguishable is if I fall, between the legs of the camel here. If I'm able to pick something that's in this space, then I'm good. That means I can't distinguish the values. However, if I happen to have generated my 0 in this area in the left hump and my 1 in the right hump, that means I can clearly distinguish both. And that's a problem, because that means an attacker knows, and you're leaking your data, right? So what you note also is that, well, so these humps are large. So that means I have a very high probability here of falling into a case where I can easily distinguish my numbers. So what is the solution there? The solution is on the right. So instead of taking a small distribution, I take a very large one. I take things that are sufficiently large. You see that the scales have considerably changed on the right-hand side, such that the humps are very, very small, or sufficiently small. So what does sufficiently small mean? So sufficiently small means that I have a very low probability of falling in those humps, and I get computational security. So my attacker could actually maybe distinguish the value, but to do that, he would have to do a lot of work, because he'd have to send up to a large number of queries just to be able to distinguish the values. So we don't have information theoretic security where we're none the wiser with the masked values. However, what we have here is we're making the work of an attacker much more difficult by making the humps as small as possible. And yeah, that's what you get with computational security. But however, the problem is now, as I told you, we have these humps. Let's go back to these humps. So if I take a very large distribution, that means that in practice, what does it mean? It means that if I have a floating point, let's say that's 10 bits long, so it's smaller than about 1024. If I need to take a sufficiently large distribution, so I need to mask using maybe 40 extra bits, because I want my attacker to be able to work very hard. So that means for a 10-bit number, I'm using a 40-bit number. So if I multiply two such numbers, then I can blow up, right? So when I multiply plain text, if I have a 10-bit number and I multiply with another 10-bit number, then I can get a 20-bit number at most. 20-bit number still is fine, because it's a floating point. It can still fit under 64 bits. But at 40 and 40, well, I'm really blowing up. And so that's an issue. So those are the kind of things that, we basically need to, on the compiler side, analyze and estimate such that we can sort of ensure that we don't blow up. So there's a little bit of, what we do is we don't really use a floating point representation. we use something that's called a fixed point representation to represent floating points in our backend. And these different number representation sort of helps us avoiding this format explosion, or we at least don't explode as quickly. And this is what we analyze statically in the compiler so that we can propagate the statistical bounds correctly to the whole program before we sending to the engine.
Yes, exactly. So I'll give a quick overview now of what the compiler actually does and how the input language looks like. Let's jump right into it. This is some source code from our language. It looks pretty much like Scala, except a semicolon is still required.
Sorry.
Well, why? It's a long story. It doesn't look really exceptional, and that's by design. We want it to be as easy to use for anyone who does not know anything about MPC. So it really looks like some linear algebra code. The only thing you'll note is there are these XOR dot things. These are, you can think of them as calls to a standard library or some primitive instructions. These things are known by the engines, known by the machines that have access to data. But so they're not known quite like this. What we're again not showing here are all these parameters, these masking parameters, sizes, which are not of relevance for a developer, but are of course very important in the actual runtime. So on top of these primitives then, we build a language on it. It is strongly typed. In fact, everything is always inlined. Everything gets constant folded, so that these primitives, that we can infer parameters such as masking sizes to the primitives when we actually generate the code. We'll get into that in a second. So when you compile a program, you just submit it as a source file, and the compiler goes through various phases. It's built like a traditional compiler for around 8 phases. So we do things like parsing, type checking, etc. And then we get into some more details where we actually do the cryptographic part. And this is where we need to check that, for example, if we multiply two numbers, that although the resulting number will be larger, that the mask does not just naively get doubled. Maybe we can, because we know something about the distribution of data, we can take a smaller mask and thus be much more efficient. This is what comes out of the compiler. So it might look a little bit daunting, and it looks a bit like assembly because this is what it is. It's assembly for the MPC engines. But we'll walk you through some what happens here so that you can understand what's going on. The first part is memory management. So right in the beginning, we said that one of the jobs of the compiler is to make sure we're as efficient as possible. And we're doing matrix multiplications. These things require a lot of memory. So we need to make sure that we can actually, so that we allocate and deallocate memory when variables are no longer used. So in blue, you see currently all the create calls of, so these are like, this is like a malloc essentially. Delete is not on the slide, it happens just below, but don't worry about that. Then we have the built-ins. So built-ins always work on containers. A container is again like think of it like a variable. These built-ins, however, so these built-ins map to what I showed here, these XOR, these language built-ins. The difference, however, is that we now show all built-ins have some extra parameters passed to them, and these are the result of the compiler. There is also all dimensions of any input variable, so these are the things you see in brown here, they all get folded, they all get replaced by the actual values. So in the end, so the example I'm showing here is we have a number of rows and a number of columns. These are taken from the input values. But however, at runtime, since it's a distributed computation, we need to, and to be as efficient as possible, we need to know the sizes of all input in advance, and that gets propagated through the program. And then finally, in red, this is actually the key part of the compiler, is inferring these parameters. So these are these magical masking values that we try to minimize in the compiler to make computations as efficient as possible. Now, you could technically write this by hand, right? But of course, that's actually what we have done right in the beginning. But using a compiler also allows us to compose programs much better. So rather than writing a prepackaged linear regression, assembly routine, you can actually build a full mathematical library with these operations and compose them to your liking. So what we currently have is the compiler only works with MPC. So this is the protocol we talked about. However, since it's a compiler and we can work on these high-level languages, it would be nice if in the future we can integrate other privacy-preserving techniques here. This is something more aspirational that we would like to get to. Currently, we are focusing on MPC. But the compiler is in a prime spot to be able to work as an intermediate for all these technologies. Finally, I want to give a quick word about our team. We're currently 6 people working on the compiler at Infer, a company. We're quite some more. We're actually growing, and the salary is not as bad as we mentioned in the example. So yes, please come talk to us if you want more details, and thank you. I think we have enough time for questions.
Yeah, great. Yeah, we're actually 10 minutes in. Wonderful. Please.
Yes, please take a microphone.
Yeah, that's pretty cool. Thanks for the talk. I'm pretty curious about I guess I will have many questions. I will come to your booth later. But about the type system, do you infer the matrix dimension, I guess?
Yes.
So if I have a mismatch of the matrix dimension during compile time, you will tell me that that's not good?
Yeah.
Wonderful.
So the compiler is it's not a Turing-complete language. Everything must terminate, and we need to know a lot of information about the input, so the shapes. We need to know sizes of the input.
Okay.
So actually, when you see this XOR input built in, you see here this X needs to be known by. We need to know that.
Okay. Okay, sounds good.
So we need to. It's important to emphasize that we need to know just the properties of the data, and of course not the data itself. The data itself is still private and secret, and will not be revealed.
And then this value that you infer that are for this complex multi-party computation you do, is it also part of the type system? This is something you infer as part of the type checker?
So that's actually a bit of a trick question and a complex question. So let me disambiguate that a little bit. So we don't encode it in the type system in our implementation. What we do instead is, through the multiple phases with a bit of partial evaluation and so on. But yeah, I guess with Scala 3 and literal types, it would be very fun.
With Idris, have you thought about Idris?
We have thought about Idris.
It's a perfect
definitely.
language for that, no?
Yeah.
Idris would be, Idris is something that I would like to experiment as well, to play around with. But I think the key really is you still at some point need something like a compiler. So you need to go from sort of a shallow embedding to a deep embedding, and actually have access to your trees. Because in particular, if you look at phase 4 here, SSA is actually very critical for us because we want to generate efficient assembly such that memory is properly allocated and deallocated. And so you need to convert to some nice form so that you can do
it makes a lot of sense. Anyway, you want more phases because you have very specific optimization to do for you.
So essentially the key part, what we're focusing mostly is anything after around phase 8. Anything before that is general compiler construction. The front end, like how the language looks, this is something we could imagine changing in the future.
And having multiple of them, right? Potentially.
Yeah, potentially,
yes.
Right.
Thank you.
Thank you. We have a few questions, yeah? Sorry.
I have several questions. First is, how is your algorithm sensitive to noisy? For example, if you want to apply machine learning, using some back propagation, for example, using exponential functions. If you just use approximation, then you add some random numbers into the input, which might make the back progression have problems. How do you solve this?
Currently, we don't. No, so this is definitely something we're working on. So whenever you need to propagate, to get some results back from another computation as input to a new computation, we need to submit a new program at the moment and save intermediate results to another place. We're working on maybe making this more seamless into
and with regards to precision, right? Of course, we're approximating, but what we try very hard to do is we want sort of the same precision, whether you would do it in plain text or with MPC. And so our current benchmarks are that we're in the 7 to 8 decimal points after the unit. So which is what our customers also expect us to have, and that's already
Okay, so you mean that you can always keep this precision regardless what kind of inputs?
Yeah, so that's what the key or the most difficult part for us is with the static analysis.
Yes.
Okay, thank you. So my next question is, what is the input for the trusted dealers in general for all of these for your libraries?
Input, what do you mean the input to the trusted dealer?
What kind of information you in general you provide for the trusted dealers?
Yeah, so the trusted, so this compiled program which comes out of it is you can think of it as a graph. It's a DAG essentially, and this gets fed into the trusted dealer. So the trusted dealer knows how much memory, so how many secret shares are ever need to be generated, generates them, and then sends them to the engines.
So you give the compiled program.
We give the trusted dealer the compiled program.
Okay. We can discuss later. I have some more questions. So my last question is, because it's a distributed computing, right? What if there are some failures happens in one of the nodes? How are you going to verify it?
Yeah, so currently the system is designed to handle large amounts of data, not large amounts of parties in it. So we'll have, we can have several parties, but we wouldn't have like thousands of parties in a computation. So if something goes wrong, we would just restart the computation.
And how do you verify if it's correct or not, right?
That's a good question.
Maybe we can just get that question.
Okay.
Sorry.
Okay.
I think it's a.
Just to summarize, so there are non-interactive zero-knowledge protocols that could independently verify the correctness of the computation. And just to give you an idea, so one of the protocols that are used there is used also in this cryptographic currency, Zcash. So it's called ZK snarks. You can do things with that.
So I don't know.
So actually, I'm very familiar with the ZK protocols because we are building a new public blockchain. We investigate the ZK protocols deeply. So right now, it's really not practical at all. If you want to provide proofs or if you want to really just work with it, it's like for one computation, it could be even seconds to generate the proofs,
So you can provide proofs. There are certain techniques in which we can provide proofs. We even did it with an external company who specializes in non-interactive zero-knowledge protocols. So, for example, the program that you saw there, for that program, we can give you a proof that convinces that provides in zero knowledge a proof that the function is minimized, the objective function in machine learning is minimized.
So if I may interrupt, please take this offline because a few more questions at the back. I thought Victor had a question.
Thank you very much.
Yep.
I think this may be going to the hard part, but so do I infer correctly that you need to estimate the ranges of these real number approximations that you're encountering?
Yes, exactly. Okay. So we have, Actually, one of the inputs is not only necessarily the size, also distribution of the data. So for certain types of computations, we need to know that.
Okay, so do type systems help that, or do you feel that kind of abstract interpretation, numerical domains are a better match?
So I think honestly it's a big mix of both. Again, for us, since so we're using sort of a cheated partial evaluation to do this, but sort of the calculus itself is so we haven't formalized this, but I think something like, I mean, you need the actual sort of distributions there. Maybe one sort of answer that gives us a probably future technique is sometimes statically estimating them using static mathematical knowledge of distributions may not be enough. So you may need to do some computations at compile time, some random sampling at compile time to get you better bounds.
Essentially some simulation.
Yeah, essentially, yeah. So I don't know if that answers your question.
Thank you.
Could you please point some public research that explain the algorithm that you are being
so yeah, definitely. So there is the sort of the main reference for what we do is called the. So unfortunately, I don't have the slides, but it's called the SPEEDS protocol. So SPDZ for the 4 authors that wrote this, and this is sort of the setting that we use, which is honest but curious with trusted dealer. That would be a good place to start. Another good place to start, I would say, is check out our repo, because we've posted a few links, and there's one other tutorial by Morten Dahl. He goes into some of the details. It's very educative.
Yeah, we have.
Sorry? Our language, do we want to open source it? So that's a very interesting question and sort of tough question, because actually we have this, So we have, the problem is, so our security model sort of tolerates some things, but there are other attacks. So particularly if I can send multiple sort of orchestrated values to the secret computation such that I can recover the other person's data. And so this is where something like a privacy budget would be nice. So you want to have a static analysis which tells you, hey, you've sort of, the computation you're doing will leak data. Yeah. And we don't have this for now. And so since for now our customers are have fairly sensitive data, we don't want them to shoot themselves in the foot just yet.
An example would be it's a no-op, the identity, or even just transpose a matrix and give me the result back. Well, you can trivially revert that. So we don't have this concept yet, but it's something which would be super exciting if we could do some research into that.
Yeah. Guillaume?
So if I understand correctly, there's some trade-off between like how complex your masking is and like how security is versus how much your computation is time, like the computation time you're going to take. So how do you like choose that trade-off?
I don't know actually the choice. Dimitar might be able to answer. We use currently a 40-bit.
Yeah. So security is actually paramount for us. Yes. I mean, let Dimitar confirm that. But the idea is, again, customers are, they need the actual some level of security, which in this case is the computational security I was mentioning earlier. So we need to make sure that all our algorithms and protocols match this security requirement. So that's the trade-off we need to make.
Yeah. So basically, if you think about standard symmetric encryption nowadays, there are standards for how many bits of security you want, and what is the amount of work that you need to do in order to break a scheme. For example, AES. So people advise like certainly over 80 bits of security. So based on that, these standards, you could define your global compiler parameters that are going to guarantee security if you follow the protocol properly.
Yeah. And we have, I think, tell me if it's wrong, but it's 2 to the 40 bits, 40 bits for online operations, so interactive queries, which is largely sufficient. For any data at rest that you could, like if you were to take it and analyze it, we're much more secure, like AES 128 or something like this.
Yes, so you want to match the security of AES 128
Okay.
to 56.
So that's actually a funny name. So our product is called XOR. And there's many reasons. One of them is XOR is from a one-time pad, information theoretic security. I mean, it's also fast and used in many cryptographic operations.
One more question at the back. Yeah.
Thanks. I have a question regarding GDPR because there is right to be forgotten in GDPR. And from the algorithm itself, it looks like if one of the employees, like on your first example, exercises the right to be forgotten, then I need to recompute the values for everyone else. And it feels like a very computation heavy in case you have a lot of users. How do you tackle that?
Well, so my answer to this is that I mean, our current use cases we don't haven't faced this issue directly because most of our current use cases are about sort of one entity managing multiple distinct but sensitive entities, right? Like a bank, for instance. So all their data sources belong to them. The law disallows them to sort of exchange things.
But I'm a user of the bank, and I can request my data to be forgotten forever by the bank. So I don't want it to be used in the training of the models. I don't want it to be used everywhere, and it's my GDPR right. So it feels like in that case, the bank will be in need of like recomputing a lot of things.
So that's why we need to make it very efficient, I guess.
Yeah,
Yes.
we don't address this problem. We are already in privacy preserving. So I don't know, maybe I don't know the exact legal details of GDPR, but is it not, maybe it's sufficient if you anonymize maybe user handles or anything before they get shared?
So what is important is that your data never leaves the bank, never leaves the source with this protocol. That's why Baker McKinsey estimated that this falls outside of the scope of GDPR.
Any other questions, or are you hungry? Yeah, no, one more question. Definitely.
Hello. How does your solution currently compares to other, technical, other solution for privacy-preserving computation, like what you can have in a TensorFlow federated and OpenMind?
Sorry.
So how does the solution from a cryptographic side compares to a TensorFlow? Was that the question?
Well, it would be more on the commercial side because your competitors today, they are people like TensorFlow backed by Google. And using TensorFlow federated, you can do secure multi-party computation.
Right. Right, I see the question. So there is a good distinction between multi-party computation and federated learning. So federated learning is a protocol where we could all collectively do a computation here, everybody in this room. So everybody computes locally on a device and then sends a local result to a server that is going to aggregate the result of the computation. So obviously, this is very different than secure multi-party computation, where you're not sending any kind of even aggregated data. You have a number of parties, they just compute in a completely decentralized, distributed manner, and then at the end of the computation, you're getting the result in secret shares. So you don't have to even reveal the result to the public or to the analyst. So it's very different. But the two are kind of very different use cases. And in the situation where, for example, you want to compute between a handful of hospitals, then secure multi-party computations for various mathematical functions is much more appropriate than federated learning. Google is interested in federated learning, obviously, because they want many parties to do a collective computation. But even from a security point of view, it's very different. Does that answer? Question.
Great. Looks like then it's time to have lunch. Thank you very much. After your time.